All right, kiddos. So now that we have some background regarding gravitational potential energy and gravitational potential at a planetary scale, let's see if we can come up with an equation to calculate the escape velocity, or the velocity required, the minimum velocity required for an object to be launched off the surface of a planet or other large body to escape the pull of that planet. Okay, so what we know in terms of conservation of energy is that the energy that our launched object has at launch must be equal to its energy that it has at any other moment in time. Okay, and we're really interested in comparing the energy that an object has at launch to the energy that that object has when it has escaped the planet's gravitational pull. And remember, we call that location infinitely far away. Okay, so the energy it has at infinity. All right, so what kind of energy does an object that's being launched have at the instant it's being launched? Well, it has kinetic energy, right, initially at launch. And even though we're saying it's probably on the Earth's surface when it's being launched, it does have some gravitational potential energy on a planetary scale because that object is some distance away from the center of the planet, right? From the center of the Earth, we'll say. And then at infinitely far away, right, we've escaped the Earth's gravitational pull. So there's no gravitational potential energy, but there is some kinetic energy. Okay, so kinetic plus gravitational potential energy at launch equals just the possibility of kinetic energy of that object infinitely far away. Okay, so the kinetic energy is 1/2 mv, and I'm going to label that as the escape velocity, v sub esc squared. And then our equation for gravitational potential energy on a planetary scale is minus g m, right, mass of the Earth, mass of your thing being launched, over r, and r is going to be specifically the radius of the Earth at the launch. Okay, and then the kinetic energy would be 1/2 m times the speed it's going at infinity squared. Okay, so here's the thing though. At infinitely far away, the escape velocity, so when we're launching an object and we want it to escape the Earth's gravitational pull, what we define as the escape velocity is the minimum launch speed for it to escape Earth's gravitational pull. So what that means is that just at the instant that the object that we're launching escapes Earth's gravitational pull, that means that object would come to rest at that point, right? So the kinetic energy at infinitely far away will be 0. Okay. So let's take this equation right here. Again, 1/2 mv escape squared minus g times the mass of the Earth times the mass of our thing being launched over the radius of the Earth. That energy at launch must combine to equal 0. Okay, at infinitely far away, no gravitational pull, no gravitational potential energy. Right, at the minimum required to get out of the Earth's gravitational pull, your object will just have 0 speed at that instant. And so that means 1/2 m times v escape squared equals the gravitational potential energy, gm, em over the radius of the Earth. Okay. Your little masses cancel out, and we end up with something that we can write for escape velocity. It's equal to the square root of 2 times universal gravity constant times the mass of the Earth over the radius of the Earth. That's an E. Okay, and so that's our derivation for an equation that we can use to calculate an object's escape velocity. Okay. All right, now let's talk about how we can use this idea of Newton's universal law of gravitation to describe how planetary bodies move. Okay, they can, planetary bodies often orbit in elliptical ways, right? Not perfect circles, but there are a lot of planetary bodies that move in a circular path. Okay, and so we can use Newton's second law, specifically Newton's second law written to describe an object in circular motion, and combine it with Newton's universal law of gravitation to come up with something that Johann Kepler was able to derive, called Kepler's third law of planetary motion. And this is for circular orbits primarily. So if there's like a planet or a satellite, like let's say the moon is orbiting the Earth in a circular path, excuse me, it's experiencing a gravitational force. The thing that is keeping that object in circular motion is the gravitational pull between it and the Earth, right? So that gravitational pull is the centripetal force. We can write these in an expanded version. The force due to gravity is the universal gravity constant times the mass of the Earth times the mass of the moon over the separation, their separation center to center squared, and that equals centripetal force. Okay, so the moon is the one that's we're considering moving in circular motion. It's speed squared over the distance from the center of the moon to the center of the Earth. Okay. So we've got a radius over here and one over here. Mass of the moon cancels out. And we end up with v squared is equal to gm over r. Okay. Now we could stop right there, but what if we substituted in for v the fact that the speed of an object moving in a circular path is 2 pi r over the period? And we can substitute that in for speed and square that whole business. Oops, that's fine. Okay, and so we get 2 squared, pi squared, r squared over period squared equals gm over r. All right, one last step. I'm going to rearrange this to be written in its famous form, where we get r cubed over period squared equals gm over 4 pi squared. Okay. And this is known as Kepler's third law of planetary motion. Really simply combining Newton's universal law of gravitation with the equation for circular motion. The important thing, though, is if you notice, Newton's universal gravity constant is constant. Mass of the Earth, constant. This could be the mass of the Earth or the mass of the Sun, whatever your object is orbiting. 4 pi squared. This is constant. So what that means is this ratio of r cubed over t squared must also be constant. Okay, so for a planetary body moving in a circular orbit, the ratio of its distance cubed to its period squared is always constant. Okay, and I'm going to give you some problems to practice using this to solve for the radius or the period of orbit for a planetary body. Okay, let's take a look at an example. And I would actually like you to pause this video and try this example on your own. I want to define a term here really quick. A satellite is in geosynchronous orbit around the Earth. Geosynchronous orbit means that that satellite is traveling in its orbit and it's staying above the same place on the Earth at all times during its orbit. Okay, and what that means is it has the same period of the Earth, right? It's going around the Earth at the same rate that the Earth is rotating, so its period is 24 hours. Okay, so what I would like you to do is try this problem, see what you guys can do, and then in a moment I'll come back and you can check your answers, so please pause. All right, kiddos, let's check your answers. So we've got a period of 24 hours or 86,400 seconds. All right, so we use Kepler's third law of planetary motion right here, and we just plug in our values. So the period squared, universal gravity constant, mass of the Earth over 4 pi, and we get a value for r. But that's not the answer to our problem. The question is, how high must the satellite be above the surface of the Earth? So that distance to the surface is that r value. That's the distance from our satellite to the center of the Earth, and we have to subtract the radius of the Earth. Okay, so it turns out the actual distance above the surface of the Earth is 3.6 times 10 to the 7 meters. Okay, and if that's true, how fast must the satellite be going? Well, you can use either just your speed for an object in circular motion equation or our new orbit velocity equation, and you should get 3,070 meters per second. Okay, so our friend Kepler, this is his third law that we've been talking about. He has 2 more laws. We really only need to worry about the third law. The first and second just say that orbiting object speed when it's in a elliptical path. Well, the first one says that objects move primarily in elliptical orbits, and that the area that 2 objects are orbiting in an elliptical path, it'll take the same amount of time, right? The same amount of time to travel this distance as it will this distance over here, the same amount of time, as long as the areas that are being swept out are constant. Okay, so that's just kind of a conceptual thing. You really don't need to know about that, but you do need to know how to use Kepler's third law. All right, so this week for homework, I want you to try some of these problems. We're in chapter 5. Take a look at the sections referenced. These are on the Google Classroom. Focus on concepts and a couple problems.